People assume reaching another planet is just a matter of pointing a rocket and pressing go. But the reality is nothing like that. Every single planet in our solar system is moving constantly, and that one fact changes everything about how you reach them. Earth is traveling at 30 kilometers per second around the sun, and any spacecraft leaving Earth carries all of that momentum with it. To reach another planet, you never aim at where it is. You aim at where it will be by the time you arrive.
The most efficient route between two planets is called a Hohmann transfer, an elliptical arc shaped by gravity that saves fuel but is never fast.
Then there is the gravity assist, where a spacecraft uses a planet like a slingshot, gaining massive speed without burning a single gram of fuel. Chemical rockets provide enormous thrust at launch but burn their fuel in minutes, leaving a spacecraft coasting the rest of the way on momentum alone. Ion thrusters are completely different. They generate almost no force but fire continuously for months, building speed slowly in the silence of deep space.
Nuclear propulsion systems are currently in development and could one day cut these travel times dramatically, but right now we are still flying on chemistry.
What most people do not understand is just how vast our solar system truly is, and the distances involved resist easy human comprehension.
The distance from Earth to our moon is roughly 400,000 kilometers, and that already took 3 days. Now consider that Neptune is 12,000 times farther away.
Every mission to every planet in history has had to solve the same fundamental problem. How do you arrive at a moving target using only the physics available to you? Teams of scientists spend years calculating the exact trajectory before a probe ever leaves the ground, and a single miscalculation can end a mission entirely. We have been solving these problems for decades. Voyager, Cassini, New Horizons, each mission a masterclass in using the physics of the solar system itself as a tool. In this documentary, we go planet by planet, from the scorching inner worlds to the icy giants at the very edge of our solar system. We start close to the sun, where the distances look small on a diagram, but the physics can make even nearby worlds brutally difficult to reach. Mercury is the closest planet to the sun, and logic says it should be the quickest to reach. But logic is completely wrong in this case. Any spacecraft heading toward Mercury is pulled in by the sun's enormous gravity and accelerates so fast that it simply flies right past the planet without stopping. To actually slow down enough to enter orbit around Mercury, you have to use Venus and Mercury itself as brakes, in a series of carefully timed gravity maneuvers. The mission took 6 gravity assist maneuvers at Earth, Venus, and Mercury itself over a journey of more than 6 years before it could safely capture into orbit. 7 years of travel to reach a planet that is closer to us than most people have ever traveled in a single direction on Earth. That is the paradox of Mercury.
Mercury is one of the most difficult destinations in the entire solar system, not because of its distance, but because of where it sits in the sun's gravitational well.
Venus is our nearest planetary neighbor, and under the right orbital conditions, it is the fastest planet to reach in the entire solar system. 3 to 5 months is all it takes to reach Venus when the launch window is right, and that window opens reliably every 19 months as the two planets align.
Venus has surface pressure 90 times greater than Earth, hot enough to melt lead instantly. Every probe ever sent to the Venus surface has been crushed and destroyed within 2 hours of landing, no matter how heavily it was built to survive.
Easy to reach, impossible to visit, Venus is the ultimate contradiction in our solar system, a neighbor we can approach but can never truly explore from the ground.
Here is a question for you. If you had to pick one planet beyond Mars for the first human mission, which one would it be and why? Mars is the only world beyond Earth that humanity is actively planning to send astronauts to, and the timeline is now measured in years rather than generations. Earth and Mars can be as close as 56 million kilometers or as far as 401 million kilometers apart.
Every 26 months, Earth and Mars reach opposition. That window is the only time when a mission can launch with enough fuel efficiency to actually reach the planet.
Robotic missions including Curiosity and Perseverance all completed the journey in 6 to 9 months, with an average of around 7 months using the standard Hohmann transfer route. For human astronauts, the one-way journey to Mars takes 8 to 9 months, and that is before the real challenge even begins. Once astronauts arrive, they cannot leave immediately. The planets have moved, and the next favorable return window does not open for approximately 500 days. Those 500 days must be spent on the Martian surface, working, surviving, conducting science, waiting for the geometry of two planets to align again. Add 8 months out, 500 days waiting, and 8 months back, and the total mission duration reaches roughly 2.5 to 3 years away from Earth.
The engineers and mission planners working on this program are not designing science fiction. They are engineering the most ambitious human journey in history. Deep space radiation, beyond Earth's magnetic field, is one of the most serious biological challenges crews will face. The psychological challenge of living in a confined spacecraft for 8 months, traveling toward a world where no help can reach you, is unlike anything humans have faced before. Mars is not a fantasy destination anymore. It is an engineering challenge that multiple space agencies and private organizations are actively solving right now. Of all the planets on this list, Mars is the only one where a human mission is not theoretical. It is scheduled, it is funded, and it is coming. The red planet has waited 4 billion years for a visitor, and within this decade, for the first time in history, one may actually arrive. Beyond Mars, the scale of empty space jumps so dramatically that journey times shift from months to years. Jupiter is nearly 1 billion kilometers from Earth, making it almost incomprehensibly far beyond anything we have discussed. New Horizons reached Jupiter in 13 months, but used its gravity as a slingshot to push deeper into space. With smart gravity assist maneuvers using Venus, Earth, and Mars as stepping stones, travel time to Jupiter can be compressed to 2 to 3 years rather than 5 or 6. Beneath those iconic cloud bands, the atmosphere extends for thousands of kilometers with no solid surface, just deepening layers of gas and liquid under crushing pressure. Jupiter's moon Europa may hide a liquid water ocean beneath its icy shell larger than all the oceans on Earth combined, making it one of the most compelling targets in the solar system. A crewed mission to Jupiter would take 2 to 3 years at minimum, pushing human endurance beyond anything attempted before. Saturn sits between 1.2 and 1.7 billion kilometers from Earth, more than double the distance of Jupiter. Cassini spent nearly 7 years reaching Saturn and became one of the most productive planetary science missions ever launched. Saturn's rings are made of billions of individual ice and rock particles, spanning a distance wider than most people can imagine. A crewed mission to Saturn would take 3 to 4 years each way, pushing human biology to its absolute limit. We are not just talking about engineering challenges at this distance. We are talking about keeping human beings mentally and physically healthy through years of complete isolation in the void. Saturn's moon Titan has liquid lakes on its surface, not water, but liquid methane, making it the only world other than Earth in the solar system with standing liquid on its surface today. Saturn sits at the very edge of what a human mission could realistically endure with current technology. Beyond it, the solar system belongs to our machines. Uranus is the most tilted planet in the solar system, rotating essentially on its side, with its poles pointing almost directly at the sun, and almost no one can explain why. Voyager 2 is the only spacecraft to ever visit Uranus, arriving after 8.5 years of travel. A dedicated Uranus orbiter mission currently in planning stages is expected to take 9 to 13 years of travel, depending on available gravity assist opportunities during its launch window. For a human mission, the outbound journey to Uranus alone would take 12 to 15 years, and the full mission, including return, would stretch to 25 or 30 years. No human, no life support system, and no propulsion technology currently exists that could make a 30-year mission feasible. Neptune lies 4.7 billion kilometers from Earth, the most remote planet in our solar system. Voyager 2 is the only spacecraft in human history to visit Neptune, launched in 1977 and arriving in 1989, 12 years. Let us put all of this together, because when you look at the full picture of solar system travel, the pattern that emerges is both humbling and strangely inspiring. Mercury takes 5 to 7 years, Venus 3 to 5 months, Mars 8 to 9 months one way, with a total mission of 2.5 to 3 years, including the surface stay. Jupiter requires 2 to 3 years with gravity assist, Saturn 3 to 4 years, Uranus 9 to 13 years for a robotic probe, Neptune 9 to 10 years minimum one way. Mercury, Venus, and Mars are the only realistic crewed destinations with current technology. Everything beyond belongs to robots. Beyond Saturn, our machines are our eyes and ears, and despite the limitations of current technology, those machines have sent back wonders beyond anything we imagined when we launched them.
Voyager 1 has now crossed into interstellar space, the first human-made object to leave our solar system entirely.
In 1903, the Wright brothers flew for 12 seconds. 66 years later, humans walked on the moon, and the pace of progress in spaceflight has never truly stopped accelerating. Every generation of space engineers has faced limits that the next generation demolished, and our era will be no different. Nuclear propulsion systems currently in development could cut travel times to the outer solar system dramatically,
turning a 6-year journey into one that takes under 2 years.
Advances in closed-loop life support, radiation shielding, and artificial gravity research could make even multi-year journeys survivable in ways that are impossible today. Solar sails, laser propulsion concepts, and entirely new physics-based drive systems are all being seriously studied at major space research institutions around the world today.
The impossible has always been a matter of time, and the generation that solves the outer solar system travel problem may already be alive and studying physics right now.
Our solar system is not a small place, but a civilization's worth of destinations, each demanding its own unique solution. Neptune is not just far, it is a monument to scale, a reminder that our solar system is vast in ways that still resist the full weight of human imagination.
These are real distances, real timelines, real physics, not the movie version, not the optimistic press release, the actual engineering reality of our solar system. Subscribe to Noxar Flux so you never miss a story. Every week, we explore the real physics and hidden mysteries of space missions just like this one.